and I'd like to thank the organisers for inviting me here. It's now nearly 30 years since I was last here, so it's a great pleasure to come back. What I'm going to talk about today is a question in one branch of geometry whose explanation requires a different branch. And if I've got time, then at the end I'll talk about the context in which I'm really interested in what goes on here, which is yet a third branch of geometry. But it depends how the time goes. So my title here is, okay, you can see the two branches of geometry which are up there. Hilbert schemes, that's part of algebraic geometry, and Poisson geometry, which of course has various forms. But there is an intersection, and we're going to talk about that. But let me start with Hilbert schemes. The name Hilbert scheme of course, covers a great variety of objects, but the sort of Hilbert schemes I'm interested in are the most fundamental ones, the Hilbert schemes of points. And we can try and introduce the idea by just thinking about unordered points in a space. So when I say a space, I mean in particular, say, a complex manifold or a smooth projective variety. So in a way, this is setting up notation. So S to the n. So this is the Cartesian product. So this is the set of ordered n-tuples in the set S. And if I take the quotient of that by the symmetric group, then I'm getting the unordered ones. So the symmetric product is this quotient space here, the space of orbits under the action of the symmetric group. So let's look at a particular case of this. So suppose we take just S to be the complex numbers themselves. So of course the Cartesian product is Cn. These are the ordered n-tuples of complex numbers. But if I want to think of them as being unordered, then I can think of them as being the roots of a polynomial, and a monic polynomial, so I could write it like this. And so you can see that actually the symmetric product in this case is actually also Cn. So if I give you these complex numbers, they run up to an, then it gives me a monic polynomial, and I can solve that and get, including multiplicities, I can get n unordered complex numbers. So in one dimension, actually, this is a smooth manifold. So complex numbers, smooth. This is a smooth manifold, and the same thing goes if you have a Riemann surface or algebraic curve, something one-dimensional. If you take the symmetric product, then you'll get something which is again smooth. Locally, everything looks like this. But then, when we move up one dimension, what happens when we consider the C2? So let's look at the simplest situation here. Let's look at the symmetric product of 2 points. So just a pair of unordered points in C2. So we're taking the product of C2 cross C2 modulo the exchange of the two factors. So it's easier to see what's going on if we actually look at if we take the sum of the two vectors here, then that of course is invariant under the involution, so we can forget about that. But then we take the difference, Z1 minus Z2, that goes to minus 1. So this is just, if you like, a change of basis, but it throws all the attention on the last factor, on C2 modulo plus or minus 1. So we're looking at vectors in C2 where we identify them if they differ by plus minus, each one is plus or minus times the other one. Now, how do you describe that? One way to do it is to look for invariant polynomials. So if we think of x, y as being coordinates in C2, then x squared, that's invariant under multiplying by minus 1, so is y squared, so is xy. And in fact, if you look at any polynomial in these two variables, which is invariant under this action, it is in fact a polynomial in these three variables. But there's a relation, and of course the relation is that the middle one, square the middle one, and it's the product of the other two. So what we can say here is that if we take the quotient of C2 by plus minus 1, we don't get anything smooth. We get a cone. We get something with a singularity at the origin. Now in one dimension this doesn't happen because, if you like, z squared is a coordinate on the quotient if z is a coordinate upstairs. But here, in two dimensions, life gets more complicated. We produce a singularity. So what one was looking for is a space which removes that singularity, which resolves that singularity. And in this particularly simple case, which is a kind of model for what goes on, we can do it in a quite explicit fashion by looking at the cotangent bundle of the projective line. So here's a projective line, two-sphere if you like, and the projective line has the three-dimensional group of projective transformations acting on it, the Möbius transformations. They are generated by three vector fields, and if I think of x as being an affine coordinate on P1, if you like, if I think of removing point at infinity from the Riemann sphere and thinking of x as a coordinate on C, then these vector fields look like this. Well, this is a basis for these vector fields. On the other hand, a fiber of the cotangent bundle is something in the dual space of the tangent space. So I can evaluate a vector field on a cotangent vector, and I get a function on the cotangent bundle of P1, which is linear in each fiber. So being linear in the fiber, this function vanishes at 0 in each fiber, which is the 0 section. So these three vector fields, I can think of them as three functions on the cotangent bundle. And the cotangent bundle of P1, that's a nice, smooth, two-dimensional manifold. And it gives me a map to C3, and the image satisfies this equation because you just see what happens. There's the x in the middle and the x squared there and the 1 there. So the result of this is that actually this smooth manifold, I can put back the C2 now, but so this smooth four-dimensional manifold has a map onto the symmetric product, which is singular, in such a way that it resolves this singularity, this conical singularity, in a particular way. What do we mean by resolving it? Well, what are the points up there that go into 0? It's the 0 section. It's just the projective line itself. The copy of the projective line sitting inside the cotangent bundle as the zeros of all those fibers. So what we can say actually, so this, if you like, this is the simplest example of a Hilbert scheme of 2 points on C2, and it has this distinguished copy of the projective line sitting inside it. So in general, if we have a complex surface, S, then if we take the symmetric product of two copies, then the singularity occurs where Z1 is equal to Z2, where the 2 points coincide. And what I showed you was that there was in that particular case, in the local case of C2, there was a resolution which replaced the point Z1, this is the single point when they coincide, by a projective line. So geometrically what you can think of is that you have these 2 points, and as they get closer, you're replacing them by, if you like, a line or a direction through that point Z1. So the projective line of all directions at Z1 is what you replace the double point by. Now that's just, so that's the simplest possible example of a Hilbert scheme. But as you can imagine, if you have more than 2 points, then there are lots of different ways in which these points can coalesce. I mean, they could coalesce like that, and then another point comes in all together, which direction. So to do it in this down-to-earth fashion is very complicated. But fortunately, algebraic geometry comes up with a description of an object which does all that for you, and that's what the Hilbert scheme is. So I've told you about the Hilbert scheme of 2 points, But in general, you can talk about on a, let's say, an algebraic surface, you can talk about the set of, or the space of the scheme, the zero-dimensional subschemes of length n. So I don't want to say anything more about it. I want to say that it's a smooth manifold of dimension 2n. So I'm going to denote it by these square brackets here, which has a natural map to the symmetric product, and it resolves all the singularities in the symmetric product in a very nice fashion. So these are spaces, because of its algebraic description as a moduli space of certain objects on the surface. These are functorially associated to any algebraic surface. So in particular, if I take a surface given by some polynomial equations, and if I vary the coefficients of those polynomials, then I'll deform the complex structure of the surface, then automatically I'll find a deformation of the Hilbert scheme. This is functorial, the association of the Hilbert scheme to the surface. So any deformation of the surface gives me a deformation of the Hilbert scheme. Well, this question was something which occurred some years ago to Barbara Fantecchi, and she wrote a paper about this, where in particular one of the main results was this, that if S is a surface, a projective surface, algebraic surface, smooth algebraic surface of general type, and as you can imagine, the words general type mean that most surfaces are like this, but if you want to think explicitly, if you want to think of a surface given by a single homogeneous polynomial, a surface in projective 3 space given by the vanishing of a polynomial, then if that polynomial has degree bigger than 4, then it's a surface of general type. And what she proved was that, so these spaces here were actually isomorphic. So we're going to meet this again. So this is you can think of it as a sheaf cohomology group or a Dolbeau cohomology group. It's a vector space which measures the tangent to a deformation. So if I'm deforming, if I have a particular complex structure on my surface, and I have, let's say, a one-parameter family of such surfaces, deforming the coefficients, if you like, then the derivative at that point is a vector in this space here. So we'll see that in a bit more concrete fashion later on. So what we can say, when I said that any deformation of the complex structure of the surface yields the deformation of the Hilbert scheme, that means that there's a natural map, vector space map homomorphism from this vector space to this vector space. And what she proved was that this was an isomorphism. And so since we know that, so we know that any deformation here gives me a tangent vector in here, and it gives me something over here, what she effectively proved was that all small deformations of the Hilbert scheme are induced from deformations of S. So that's, that's a nice situation. It's fine. You know that if you have this Hilbert scheme, somehow or other it's defined by algebraic equations, but you're not going to get anything new by trying to deform that. You'll only get the same thing as deforming the algebraic equations, the coefficients, if you like, of the polynomial of S, and then taking the Hilbert scheme of that. On the other hand, if you look at her methods, and you don't look at a surface of general type, then you find that actually take the simplest possible algebraic surface, the projective plane, and that is totally rigid. It has no deformations at all. On the other hand, this space here actually has a 10-dimensional space it's a 10-dimensional vector space. And so the question that arises is, two questions. Why is that true, and how is that true? What are these deformations, this new type of deformation of this Hilbert scheme, which doesn't occur for a surface of high degree, but something's going on for P2, and we've had other surfaces, which is not happening for a surface of general type. So that's the puzzle, if you like, that I want to try and address. And, well, there are 2 points to it. One is, well, this is only, first of all, this is only a vector space. And I told you that if I have a deformation, a one-parameter family of deformations, then the derivative of that defines a vector in this vector space. On the other hand, it's not in general true that any vector in here can be integrated to a one-parameter family. So that's sometimes there are obstructions. So one question is, first of all, can we actually, if I take one of these 10-dimensional space of vectors, can I actually realize it as the derivative of a genuine deformation of a complex structure in the Hilbert scheme? And secondly, if I do, what am I going to get? How do I describe this this deformation? It's not obtained by changing any coefficients on P2. As I say, P2 has no deformations whatsoever. So that's the question, that's the puzzle. And the answer involves Poisson geometry. So here I'm thinking of holomorphic Poisson geometry. And so what does that mean? So I'm still within the realm of complex manifolds. So what is a Poisson manifold in this holomorphic sense? Well, it's a section, so I'm using this is a holomorphic section, that's what the H0 means, a holomorphic section of the second exterior power of the tangent bundle. So we're usually used to, in differential geometry, working with the exterior algebra, exterior powers of the cotangent bundle. This is the opposite sense. It's the second exterior power of the tangent bundle. And when you've got such a tensor, well, you can take let's say a local holomorphic function and look at its derivative, and then you can evaluate this. So this is a skew symmetric form on cotangent vectors. So you can evaluate on the two derivatives and get a holomorphic function, and that's the Poisson bracket. Poisson bracket of two functions. Here, because we're on a complex manifold, which I'm assuming is compact, then we can't talk about global holomorphic functions, so we have to talk about the local holomorphic functions. Another way of saying that is that describing the Poisson bracket is to say that this is sigma here gives, if you like, by contraction, a map from the cotangent bundle to the tangent bundle. And then if I have a function, I take its derivative and apply sigma, and I get a vector field. So this is the Hamiltonian vector field for the function f. So normally speaking, or when I say normally, it depends what area of mathematics you're working in. If you're working in symplectic geometry, which is perhaps more familiar territory than Poisson geometry, then Hamiltonian vector fields are, of course, very, very common. Well, you can define them using a Poisson structure. You don't need a symplectic structure. Symplectic structure will be the situation where the Poisson structure here was non-degenerate, where it's a non-degenerate bilinear form on T, and then being non-degenerate, it identifies T with its dual, so you can think of it as in the dual sense. However, I mean, the Poisson tensor is not just this. There is an integrability condition, which can be expressed in different ways. One of them is using the higher degree generalization of the Lie bracket, which is the Schouten bracket of two tensors, skew-symmetric tensors, which lives inside this third exterior power. Or perhaps more concretely, it's this, that if you take the Hamiltonian vector field of F and the Hamiltonian vector field of G, and you take their Lie bracket as vector fields, then that should be the Hamiltonian vector field of the Poisson bracket. So that's the most convenient way of talking about this integrability condition. And if sigma were non-degenerate, then the integrability condition would be that its inverse, or the corresponding section of the second exterior power of the cotangent bundle, is a closed two-form. Anyway, that's what a complex or holomorphic Poisson manifold is. And how do you find them? Well, if S is a surface, if it's a two complex dimensional manifold, then this is totally zero because this is the third exterior power of a vector bundle of rank 2, so that vanishes. So there's no integrability obstruction. So all you have to do is to find the holomorphic section of this vector bundle, which is now just a line bundle. It's a rank 1, and it's called the anti-canonical bundle. So any surface that you have which has an anti-canonical bundle with non-zero holomorphic sections is a Poisson manifold. Of course, the Poisson tensor could be 0, so you could say that any surface is a Poisson manifold, but they're not, obviously not so interesting. So that's a surface. If you go to 3 dimensions, then you're looking for a section of this rank 3 bundle now, but it's canonically isomorphic to this, so this is the cotangent bundle twisted by this anti-canonical bundle. And then the integrability condition is that it's the Frobenius integrability condition for a foliation. Okay, so this is if you like, a meromorphic one form, and it defines a singular foliation because this Poisson tensor could vanish somewhere, but the integrability condition is the familiar foliation condition, Frobenius integrability condition for a codimension 1 foliation. And the leaves, if you look at d theta and restrict it to the leaves of this foliation, then that gives you a symplectic form along the leaves. So that happens more generally. You have symplectic leaves for a Poisson structure. Now, one of the things which I've benefited from in coming here is talking to Pereira here, who pointed out this recent paper of his, which is a very interesting paper. In particular, they're looking at foliations, singular foliations, but it includes a classification of Poisson structures on a class of threefolds called Fano threefolds. So that's if you want to look at examples of this, then look at this paper. Okay, so that's the situation in 2 and 3 dimensions. But of course, the Hilbert schemes start in 4 dimensions, so they're 2n dimensions. And in fact, they're useful because of a result of Bottochin, who says that actually, if you start with a Poisson surface, so if you take an algebraic surface with an anti-canonical section, then in fact it induces one naturally on the Hilbert scheme. It's easy to see why that should be true because if you look at before you take the quotient, if you look at the product, if you just look at the product of this surface S with itself n times, then in local coordinates you can see that you can just write this down. Here is a Poisson structure. Well, here is a tensor. It satisfies the integrability condition because these are independent variables. If you look at the bracket, you've got to differentiate this with one of these, and this is independent. It's just a function of y1 and y2. It's independent of x1 and x2. So the bracket condition is automatically satisfied. This tensor is obviously invariant under the symmetric group, permuting these factors. So the main point is showing that it actually extends to this Hilbert scheme. Well, there are other ways of saying it. You can define the tensor directly in terms of the algebraic geometry, but then you have to prove that it's actually integrable, and so you need to go back to this local description. So a Poisson structure on the surface gives rise to a Poisson structure on the Hilbert scheme. So, beyond 3 dimensions, we have a lot of examples of Poisson manifolds because of this. But now, once we establish this, then that P2, for example, projective plane, that has a Poisson structure because the anti-canonical bundle there is of degree 3 and has lots of sections. So actually, the Hilbert scheme of P2 has a lot of Poisson structures as well. So that's one reason why it's good to start looking at deformations. If we're interested in deformations of Hilbert schemes, then let's look at the deformations of Poisson manifolds. So, okay, so here is the way that ever since Kodaira, this is the way in which you can set up the problem of deforming the complex structure on a complex manifold. It's a very effective way of doing things. I mean, it's an existence theorem, or non-existence, depends. But it doesn't give you coordinates, or anything. It doesn't give you equations, but it tells you what's happening in differential geometric terms. So this equation here, this Mura-Cartan equation, is what you need to solve. So what does it mean? So with this phi here, this is, if you like, a one form of this type, 0-1 form with values in holomorphic vector fields. So these coefficients, phi, j, I bar, are just C-infinity functions. And if you have a solution to this equation here, so what this bracket here, it means that we're taking the Lie bracket of this. So we're thinking of this as a vector field with values in some bundle. We take the Lie bracket on the vector field part, and then we take the exterior product on the one form part. So this is a 0-2 form with values in vector fields, and that's the same as d bar. If you take d bar of this is again a 0-2 form with values in the holomorphic tangent bundle. So suppose you can solve this nonlinear differential equation. Then if you write xi bar as this vector field, so it's a mixture of d by dzi bar terms and d by dzi terms, then this is equivalent to saying that these vector fields commute. And that, with the Nylander-Nuremberg condition, is equivalent to saying that these vector fields span the 1-0 or the 0-1 vector fields of a complex structure. Put another way, that you can find coordinates such that these xi bars are linear combinations with C-infinity coefficients of d by dwi bar. So that's the integrability condition. Now, you need some linear independence, which means that you always think of phi as being small in order to get these to get the right linear independence. Anyway, so that's the equation, and so what do? So you look for an expansion of phi in terms of a deformation parameter t, and you try and solve this term by term. And if you can do that, then you can appeal to elliptic theory of elliptic operators, Green's functions, and so on a compact manifold to prove that you can find a convergent sequence, convergent series for t sufficiently small. So that's the general idea, but you can get into problems in solving this recursively. On the other hand, the first term, of course, so we're starting with this linear term here. Then, of course, the first term in the quadratic part, it will be quadratic. So the linear part of this is just a linear equation, d bar phi 1 equals 0. And that describes this a class in this, the Dolbeau representative of a class here, which is when I told you earlier that the derivative of a deformation gives me a vector in this vector space. This is what we get. So this is how you get it. And this is called the Kodaira-Spencer class. So what happens is this, that if we're on a Poisson manifold, then we have this Poisson tensor here. Suppose I choose a differential form now of type 1-1, so it involves dzis and dzj bars, which is closed. Then that defines me a class in this cohomology group, this Dolbeau cohomology group. And then I can contract one on the other and get what is potentially a Kodaira-Spencer class. So here I've written it in local coordinates, okay, just the contraction there. So given a 1-1 form and a Poisson tensor, I can contract and get something which in principle I might be able to deform. It might be the tangent to a genuine deformation of the complex structure. Well, might be, in fact it is. So there's a theorem here, so I need this. So this property here, this dd bar lemma, that's a very mild property, every Kähler manifold satisfies that property, then what happens, in particular any projective algebraic variety, smooth, then it turns out that any class in here, any potential derivative of a deformation is an actual derivative. In other words, it's unobstructed. You can integrate it. You can solve those equations term by term and integrate this to a one-parameter family of deformations of complex structure. So I figured this out because of a similar theorem, which I may talk about later in a different context. But then somebody pointed out that actually it's the same argument that Bogomolov used many years ago, 1978, in the context of holomorphic symplectic geometry. And I have only myself to blame for this, because this paper is a kind of famous paper because one of its main results is incorrect. On the other hand, there are lots of things in here which are correct, and so there's a lesson there that we should look at the whole of the paper and not just one result. So the incorrect one was that he basically concluded incorrectly from some arguments in there that there are no hyperkähler manifolds, irreducible ones in dimension bigger than 2, which is definitely wrong. Anyway, so the argument is really Bogomolov's argument, but adapted to the Poisson situation. So let me just show you how it goes. So I'll just show you how you solve the quadratic term in t in this equation. So this is what we have to solve. So here we've already got these two linear terms here, but then the bracket is quadratic in t, so I've got to match it this way. So I have to look at this, and I have to find a phi 2 such that d bar of it is equal to this. So locally, omega is a 1-1 form, a closed 1-1 form. That means that locally I can write it as curly d of a 0-1 form. So I can write it locally like this. So I have these C infinity functions, aj bar here. And then if you write this Kodaira-Spencer class, this contraction of the 1-1 form with the Poisson tensor, the right way, you can see that it's effectively the Hamiltonian vector field of aj bar times dzj bar. I'm using the summation convention all the way through here. So this is a convenient way of writing that first order deformation. So now when I take this bracket, so this is the Lie bracket on the vector field part. So I've got the Lie bracket of two Hamiltonian vector fields. And you don't need to worry about the fact that aj bar is not holomorphic, because I'm just taking the d by dzi part, and then sigma only differentiates in the d by dzi direction anyway, so you can forget about d by dzj bar. So what I'm saying is that actually the bracket, the Lie bracket of these of terms like this, is actually, by the integrability condition, is the same thing as the Hamiltonian vector field of the Poisson bracket of these two locally defined functions. And now what you can say is, well, that's all very well, but these are only locally defined functions. On the other hand, the Poisson bracket involved taking their derivatives, their curly d derivatives, and evaluating the Poisson tensor. So actually this, what looks like a locally defined form is actually globally defined, and all it is you take the 1-1 form, you square it and get a 2-2 form, and then you contract with sigma and get a 0-2 form. So this is where this integrability condition for the Poisson structure comes in, and what we've got here is, sigma is holomorphic and omega is closed, so this is a 0-2 form, which is d bar closed. Now, if I take d of it, then the dd bar lemma says, well, if you know it, it doesn't matter anyway, it says that if it's d exact and d bar closed, then you can write it as dd bar of something. So you write it as dd bar of something, and plug that in, and that solves this equation. So that's the first term, and then, as you might imagine, you have to set up the proper inductive process and run this argument again, and it gives you all subsequent terms. So it's a simple argument, really, but uses essentially the integrability property of the Poisson structure. And now if you look at these deformations, and you look at them more closely, you see that there's some interesting things going on. And these are features which would not have been present in the case that Bogomolov was looking at, in the holomorphic symplectic case. So first of all, you find that all of these deformations are actually themselves Poisson manifolds. So there's a very natural way of using the original Poisson structure and the new complex structure, after you've done this deformation, to define a new Poisson structure. So each one it's got a new complex structure, and it's got a new Poisson structure. Also, that if you look at the places where the Poisson structure vanishes, then that actually, it stays the same. I mean, inside this C infinity manifold, it's the same subset, but not only that, it has the same complex structure. The complex structure of the zero set of sigma is unchanged. In fact, there's a more general statement, which is that the Poisson tensor, it can drop rank. I mean, here I'm thinking of it dropping rank all the way down to 0. It's a skew-symmetric tensor, so it drops rank by 2 each time. And this gives you a decomposition, a stratification of your Poisson manifold. And that stratification is also remains the same under this deformation. So, for example, in dimension 3, I said that what we had was a singular foliation. Well, in that case, the foliation structure is unchanged under the deformation. What's happening is that the complex structure of the ambient space is changing. The complex structure on the leaves is changing, even though the subspace is not changing. But actually, when you get to the singularity of that foliation, when you get to the place where the Poisson tensor vanishes, that's not changing, but nor is its complex structure. So a lot of the qualitative features of the Poisson structure are retained in this deformation. And then, finally, that if you impose this condition, so this is not such a big condition, this is really, if the DD-bar lemma holds, this is like saying that there are no holomorphic 2 forms. Well, it's very difficult on a complex manifold to have holomorphic bivectors and holomorphic 2 forms at the same time. So under these circumstances, what you find is that you make this deformation. So you have this one parameter. You start with your given complex structure. You're deforming it. You have this t. And then if you look at the derivative of the deformation at t, or if you like at t equals a, then that again is written in exactly the same way as the one that we started from. The Kodaira-Spencer class at t equals a is given by taking this Poisson structure, which appears in the deformation, and contracting it with another 1-1 form. But it's a 1-1 form with respect to the complex structure at this point. And in fact, it's got the same de Rham cohomology class as the original one. So with this condition, it means that every degree 2 cohomology class is actually of type 1-1, whichever complex structure that you have. So these are very special properties of this deformation. And you can look at lots of examples and see what's happening, but I don't want to do that now. Okay, so now let's go back to Fantechi's argument, and let's see why she concluded that for a surface of general type, these two groups are isomorphic. And so this is really what happens. So there's an exact sequence. So here are the infinitesimal deformations of the complex structure on S. Here are the infinitesimal deformations on the Hilbert scheme. And there's this extra term here, which, for a surface of general type, disappears. So this is her argument. If you're interested, well, I mean, this is for the experts, I suppose. Here's a sketch of what she does. So she looks at the Leray spectral sequence for the back from the Hilbert scheme to the singular symmetric product. She looks at the direct image, the first direct image of the tangent bundle of this. That's supported on the singular locus, which is where 2 points coincide, or at least 2 points coincide. The smooth part of the singular locus is where only 2 points coincide, and there you have a map down onto the surface itself, and this sheaf is supported on this, And over here it's isomorphic to the pullback of the anti-canonical bundle on S. And then you're looking at H1s, so there's some kind of codimension argument and Hartog's type theorem, which says that as far as H1s are concerned, you can forget about all the other bits in this, all the other parts in this here. But that's not an important issue. So the important point is this, that so this is the general picture, and so what do we see now? We see now that this space here, which appears in this long exact sequence from the array spectral sequence, it actually it defines what? Poisson structures on the surface S. So what can we say? We know that if we take a Poisson structure on S and we take a cohomology class, a 1-1 cohomology class, that's going to give us a deformation of Poisson structures on the Hilbert scheme. Well, how should I put it? Let me put it another way. A Poisson structure on S gives me a Poisson structure on the Hilbert scheme, and I know that if I take a cohomology class, the degree 1-1 cohomology class on the Hilbert scheme, then I can deform that. So long as that class is non-zero, so long as that contraction is non-zero, I have a genuine deformation. Well, it turns out that if you use what's got the cohomology class of the exceptional divisor, the divisor which maps down to the singular locus on the Hilbert scheme, then this actually gives a splitting of this exact sequence. So in particular, in the case of S equals P2, this thing vanishes. This is injective and surjective, and so actually the 10-dimensional space of sections of the anti-canonical bundle gives us this a 10-dimensional space here, and each one of those is integrable by the deformation theorem. So we have some deformations, some genuine deformations of this Hilbert scheme, which are coming from somewhere, but they're not coming from deformations of P2. So here, okay, so what do we need to define this 10-dimensional space? Well, the first Schoen class of P2 is 3, which means that if I look at holomorphic sections of the anti-canonical bundle, they're given by homogeneous cubic polynomials, and there's a 10-dimensional space of these. So 9 dimensions describe a cubic curve in the plane, and then we have one extra degree of freedom to describe somehow these deformations. So what we're saying here, what I'm saying here, is that actually, if we really want to understand these deformations of the Hilbert scheme, then we've got to understand how we can obtain them by taking a cubic curve in P2 and an extra parameter, which is a bit mysterious at the moment because it only appears in an infinitesimal situation so far. How do we get that and the single parameter to define a deformation of this complex manifold? And the answer to that lies in yet another branch of geometry, in non-commutative algebraic geometry. So here, it's really this paper of Nevins and Stafford a few years ago, who discussed non-commutative projective planes. So these have been around for quite a long time, and what they are that you think of the projective plane as being the projective space of C3, the one-dimensional space of C3, and you want to deform the polynomial algebra in 3 variables, which defines the algebraic structure on P2, into a non-commutative algebra. So what that means is deforming the relation. So a commutative algebra is where, if you think of the product of 2 generators, so you think of x, y, and z as being generators of this the standard algebra, then the fact that they commute means that the relations are given by the, if you like, the skew symmetric tensors inside here. So you quotient out by the relations to get the multiplication. If it's commutative, then you're going to quotient out by the skew symmetric part. So the idea is that you're going to get a a copy of C3 inside this tensor product, which is not the skew-symmetric part. This is going to define you a non-commutative algebra. And then what Nevins and Saffer do is they set up the whole mechanism, which is well known in the commutative case of the mechanism of constructing vector bundles on projective spaces. They do it for this non-commutative algebra. Now, the one that interests us is a particular moduli space of rank 1 modules over this non-commutative algebra with certain invariants. Well, I don't want to go into the details of that. But the point is that they produce a non-commutative monad description. So monads are the way in which people study vector bundles, stable vector bundles on projective spaces. And using that monad description, they get a very concrete or reasonably concrete description of an algebraic variety, which they say is a deformation of the Hilbert scheme. Well, I want to describe what they do, but I want to describe it in without necessarily thinking of this non-commutative algebra, because it's very interesting what they do, because they go into this non-commutative realm, and then they come back, and what they find is an ordinary algebraic variety, an ordinary projective variety, which is parametrizing non-commutative objects. But they're not telling me that this is a non-commutative projective plane or anything like that. So the end result of what they're doing is actually producing something which is very concrete and commutative, if you like. But they go via this non-commutative picture. So I'm just giving you the answer. But it's easier to see the answer geometrically if you forget about, if you just think of it in these terms, that if you, instead of having V equal to W, if you just think of having three-dimensional complex vector spaces, and a homomorphism from one of them, from U into V tensor W, then so that, for example, could be the relations in an algebra when V is equal to W. But the geometry that arises out of this is very classical. So you can think of it in three different ways, three different interpretations. One of them is this, that I want to think of this part as a 3 by 3 matrix, but it's got values in linear forms on U. Okay, so choose a basis, if you like, choose a basis for V, a basis for W, and then you've got a 3 by 3 matrix of linear forms on U. So if I take the determinant of that and set it equal to 0, then that gives me a homogeneous cubic equation, and that defines a cubic curve inside the projective space of U. So that's the projective plane described by U. On the other hand, if I take a point on that cubic curve, then the corresponding matrix is singular, and so I can look at the degeneracy subspace, or put another way, actually, this should be a dual, actually. I can think of this as a homomorphism from V dual to W, and then I can look at the kernel of that homomorphism. Generically, that gives me a one-dimensional subspace of V dual for each point on the cubic curve. So that actually defines me the same abstract elliptic curve, but sitting inside a different projective space. And equally, I can do it on the other side, and I can think of the curve sitting inside this projective space. So I have one abstract curve, which is represented as a cubic in three different ways. So what that means is that my curve, my elliptic curve C, has three distinguished degree 3 line bundles on it, given by the sections, the sections by lines in each of these projective planes. There's a relation between them, but ultimately what it comes down to is that data, U, V, and W, modulo the general linear groups acting, up to equivalence is given by an elliptic curve together with a translation, the difference of these two line bundles here. So this is what their construction consists of. So you take, so if you're trying to construct this deformation of the nth Hilbert scheme of P2, so what you do is you take matrices like this. So this is n by 2n plus 1 matrices with values in this three-dimensional space V, and then the other way around with values in W, and then you look at this these quadratic constraints, you look at BA, which sits inside here, and you insist that it lies inside the U, which sits inside V tensor W. So this is a lot of constraints, and then you divide out by the obvious actions of the general linear group, and that means that you have to impose some stability condition in order to get a variety, and then this, they say, is a deformation of P2, of the Hilbert scheme of P2. So this is very nice. So this is, if you like, a description, at least of some deformations of this Hilbert scheme. And it depends on the things that we know from the deformation theory that the deformations depend on. It depends on an elliptic curve and a parameter. So all we knew originally was that it depended on a cubic curve and one parameter. But in fact, you can understand that parameter in various ways as a translation on this curve. Well, this is all very well, but actually to anybody who's worked with vector bundles on projective space will know that however appealing this kind of description is, it doesn't actually give you, for example, nice equations to be satisfied to describe what you're getting, because you have all these constraints, all these quadratic constraints, and then you have to take the quotient by these large groups, and it's often very difficult to actually get any information, any sensible information about the quotient space, the moduli space, from this description. It's in fact, when this was implemented all those years ago, 30 years ago in the construction of instantons, we said instantons depend on linear algebra, but actually if you want to know any detailed information, it's very difficult to abstract it from it. It's the same problem here. So I wanted to finish by describing something in more concrete terms, in the simplest possible situation. Okay, there we have it. We have these two parameters, the modulus of the curve and the translation. So I wanted to go back and look at the two-point Hilbert scheme and give you an example of how you actually can, by using all this information, describe with equations essentially the deformations of this. So we start with the ordinary Hilbert scheme of 2 points on P2. So what can you do with 2 points in the plane? Well, you can join them by a line. And then you can think about duality in projective geometry. That if we look at all the lines, so there's a duality between points and lines. Okay, so we have the dual projective space is a projective space of whose points consist of lines in this space here. So the dual picture of this is 2 points with a line going through them. The picture of this in the dual projective space is 2 lines intersecting in a point. And when you do it that way, you can say, well, that has another description. That's a degenerate conic. Okay, so it's a conic which consists of 2 lines. So this is one way of looking at this symmetric product. So if I now think of the 6-dimensional vector space of symmetric 3x3 matrices, then these are the equations of conics in the plane. Then the singular ones are given by the vanishing of the determinant of that. So that's a cubic condition. So we have this 6-dimensional vector space, so there's a 5-dimensional projective space, and a cubic hypersurface given by the vanishing of this determinant. So the singular conics consist of this, are parameterized by this cubic. It's not a smooth cubic, and so the conic can be a pair of distinct lines, or it can be a double line. So the rank 1 conics consisting of double lines, that's the singular locus of this cubic, which is a copy of P2 sitting inside P5, and that's this Veronese surface. So what happens here is that actually the rank 1 conics are where the 2 lines coincide. Remember, they were dual to the 2 points. So effectively the Hilbert scheme is actually a resolution of this singularity. But the point is that we have to explain the resolution, but we have algebraic equations which describe this symmetric product as a cubic fourfold in P5. So now turn on the deformation. So what do we need to deform? Well, we need to choose a Poisson structure on P2, so that means choosing a cubic curve, and we have to then take the induced Poisson structure on P2 on the Hilbert scheme, and then we're going to take a class in the cohomology. Well, this, as I said before, we take the exceptional one to get a non-trivial deformation, and we make this deformation. And so I now want to give you a description of, in algebraic terms, of what that deformation is. So now we take all 3x3 matrices, not just symmetric ones. So this is a 9-dimensional vector space. And you look at the singular ones. So you look at the determinant equals 0. So this is now a cubic hypersurface in P8. So it's a 7-dimensional one. Inside this, you have the rank 1 matrices. So these are of the form V tensor W, if you like. And it's clear that that's then a copy of P2 cross P2. So that's sitting inside this cubic hypersurface, and this is the singular locus of this cubic. And then you impose 3 linear relations on this. So you intersect with a copy of the projective plane projective 5 space inside P8. And that gives us a cubic fourfold. And in fact, what you see is that when you intersect, if you impose 3 linear conditions on this P2 cross P2, what you find is that actually you get a curve. So this is 4-dimensional. You're imposing 3 linear conditions on it. You actually get a curve inside here, which is an elliptic curve which lives in 2 copies of P2. So you can think of it as a cubic together with a translation. Or put another way, if you normalize it in a suitable way, you can think of it like this, taking the standard embedding of a cubic in P2 by the Weierstrass P function, and then the translation like this. So this is, if you like, a model for the elliptic curve in P2 cross P2. And then this T is going to be the deformation parameter. And then, what are the equations? What are the linear equations? 3 linear equations. Well, if you write things in terms of theta functions, maybe not this basis, but a similar basis for theta functions, then these are the equations, if you like, the 3 equations on 3x3 matrices which describe this deformation of the Hilbert scheme. Now, why? Now, did I really work that out myself? No. Where has it come from? Well, it's come from the old paper of Sklianin, where he actually wrote down, using theta functions, the relations in his so-called Sklianin algebra, which is the generic version of these Artin-Skelter algebras. So for a non-singular elliptic curve, this algebra was written down in terms like this. The relations were written down in terms like this by Sklianin and Odieski, maybe later, very concretely. But so here, very explicitly, you have to resolve the singularity, but here very explicitly is this deformation. The deformation parameter is given by this translation T. So you can even think of this as deforming a commutative algebra to a non-commutative algebra. You might want to think of T as being like a Planck's constant in some sense. Okay, so that tells us, what does it tell us? That actually, in fact, you can, in certain circumstances, write down these equations for these deformed objects. So they're not just abstract things out there which depend on somehow on an elliptic curve and a translation. You can actually use that data to write down the equations. Well, I hope if I can have just the last few minutes, I want to just explain what the true context of this was in terms of one of my research interests. And this relates to, if those of you who were at the the geometry session yesterday to the talk of Jeff Street. So this concerns generalized Kähler manifolds. So now we're in looking at complex manifolds, but we're looking at Hermitian structures on them. So a generalized Kähler manifold is a manifold which has a metric G, which is Hermitian with respect to two different complex structures. And there's a relationship here, so it's not a Kähler metric in general. The Hermitian forms are not closed, but they satisfy this relation. So there's a Hermitian form corresponding to I plus, Hermitian form corresponding to I minus, but these three forms are the same or opposite. And one of the key points about these is that actually if you look at the commutator of these two endomorphisms of the tangent bundle, then it's the real part of a holomorphic Poisson structure, if you raise indices using the metric. So holomorphic Poisson geometry is fundamental to the study of these generalized Kähler manifolds. And so one of the problems is how do what pairs of complex structures go together in one of these generalized complex manifolds? If I just take a complex manifold with a holomorphic Poisson structure, can I choose any other complex structure? Anyway, there was a theorem a few years ago by Goto, phrased in terms of generalized geometry, differential geometry, which actually implied that which motivated me to look at this deformation theorem. Because one of the corollaries was that if you took my omega to be a Kähler form, and you started with a Poisson structure, then his theorem says that actually you can deform the ordinary Kähler structure to be a generalized one. But in fact, if I look at what we've been talking about today, what happens is that if you start with the 1-1 form to be real, to be a Kähler form, and you do this Poisson deformation, then what you find is that this tensor here, which gives you the deformation of the complex structure, is built out of the Poisson structure and another form here, which, okay, there are all sorts of terms here, but this is a 1-1 form, and it starts with t times the given form. So, for example, and you can show that these other omegas, if t is real, these other omegas are real as well. So if omega is, well, okay, so what is the result? So the result is this, that actually if you do this, if you take omega to be real, and you do this deformation with real t, then if t is small enough, you choose a pair of complex structures within this deformation, then it turns out they are complex structures for a generalized Kähler metric. And what is the Hermitian form? Well, the Hermitian form, it turns out rather surprisingly, is precisely this form here. So in other words, the 2 form which appears here in producing the deformation actually is the 2 form for the generalized complex structure. So this is a way of actually replacing part of Goto's arguments, but having a little bit more control over what the complex structures are. They're quite closely correlated, and as we saw, the complex structures, the Poisson structures are very closely related. Their qualitative property is the same, even though the complex structure is changing. And in the examples that we've been seeing, the modulus of the elliptic curve is unchanging in this deformation. There's only some other information, the translation, which is changing. So I think this gives us a little bit of extra hold on properties of holomorphic Poisson manifolds in this context of generalized geometry. Okay, well, I'll stop there.